All right, everyone, it's 1400 hours, 2 p.m. Time to start. You are in the Measurement Analysis for Protocols Research Group in the IRTF. If you're new to the IETF meetings or the IRTF, welcome very much. I'm so glad you were joining us today. You should be signed in on either the full client Meet Echo linked in the agenda, or scan the codes at the microphones to sign on your phone. That's how we take attendance and shows that you were here and we get the right size rooms and things. So please do that sometime during the session. Also, we're in a tight schedule today, so use the chat in Meet Echo. There's 2 word bubbles at the top. Click on that. Especially the speakers that are visiting here. If people are talking about your paper, you'll see it in the chat. So if you don't have time to talk to them during this session, you can find their names and contact them outside by email or whatever after it. So feel free to use the chat, especially if I have to apologize and cut you off at the microphone if we're running out of time. So I'm the co-chair, David Plonka. I'm with WISNET. This is
Mia Kulevin. Hi.
And Miri and I have the wonderful opportunity to be kind of ambassadors between IRTF and the IETF and the academic community. So we have we think a pretty nice program set up for today. The front matter here is, this is the IRTF Note Well, Privacy and Code of Conduct. Behave yourselves, be nice to people, especially since we have a lot of newcomers at this. Make sure they see our good sides. There's links here. If there's any trouble with interacting with people, you can contact us. You can contact the Ombuds team linked here. And let's move on from that. The goals of the IRTF, as you might have heard if you went to the other IRTF meetings, we are a research organization, not a standards body or standards creating organization. We use all the formalities sort of with the way the IETF works, but we do not do standards. We're a little looser with the way things work, but focused on research. Administrivia, if you want to follow up and get the calls for future meetings, whatever, make sure you get on our mailing list. It's super low volume. Most of the things that are on there are just the calls. That's one of the things we have the hardest time people knowing that we're meeting. So Miri and I invite some speakers. Other people submit their contributions themselves. And those are the 2 ways you get to be in MAPRG. Meeting tips, I think I said this already. Get an on-site tool. If you're running it, be sure your microphone and video are off if you're it's not your turn. But other than that, that's your tool for the meeting today. So the agenda, it's packed. There's 5 minutes spared for question and answers in here, so we're going to zoom through this. I'm going to refer you to the agenda link to get it yourself. But what we've got here is a set of invited talks from IMC 2025. Some Chinese speakers from China didn't get to the meeting, so we're having them here instead. But these are ones that Miriam had invited. We've got 4 other talks, heads up about other activities in the IETF coming up, and then the 2 unique opportunities. One of the talks today will be you'll see a preview of something that's already been accepted for IMC 2026 later this year. And that's partly enabled by IMC switching to two times a year where they're accepting papers. So some papers for IMC late this year have already been accepted, and we'll show it to you today, thanks to the speaker. And then lastly, there's a talk about VPNs and IPv6. This is also unpublished work. So this is a place where if you're an IETFer, or if this is IPv6 and VPNs are your thing, you might be able to help out the author. So be polite, but please do that in the chat or talk to her afterwards. So up first, we've got Yushi. So if you could come up, I'll put your slides up here and pass you the clicker, and you'll have 5 minutes. All right, you're ready to go.
Good afternoon, everyone. I'm Yuqi from Nankai University. And today I'd like to give a talk about 16 cybersecurity studies conducted by my supervisor, Xiang Li, over the past 3 years. Each study was published at a top-tier security value, and each one informs an IETF draft submitted to DNS OP working group. So how secure are DNS server implementations? The short answer is there are widespread exploitable divergences. Because the DNS specifications left room for flexibility, and the different implementations make different yet reasonable design choices. Unfortunately, attacker can weaponize these subtle gaps. The scale of this issue is massive. Across our studies, we found over 90 CVEs and 6-level attacks, with amplification factor exceeding 20,000 times, and almost every major DNS vendor is affected. Why is this happening? It's not bad coding, it's a systematic attack surface. When high-level principles translated into code without standardized checks, attackers can use these gaps to launch attack. And so to address these issues, we map 6 attacks to 6 specific drafts. As you can see in this table, they cover 3 areas: cache delegation, query handling, and packet pre-process. Instead of going through all 6, I will just highlight 2 examples. The first is DNS bomb. It was published at IEEE Security and Privacy. This attack turns beneficial DNS mechanisms like timeout aggregation into a person DOS weapon. You can think it of Kamehameha energy blast like in the Dragon Ball. Attackers first accumulate queries, and the receiver then amplifies them through aggregation, and finally concentrates the blast by releasing all responses simultaneously. Our BCP draft proposes response pacing and short timeouts. Take Unbound, for example, it can reduce the amplification factor by 99%. The second is reverse date from CSS 2025. Here, a one-sentence ambiguity in RFC 7871 ECS extension revives a 20-year-old cache poisoning attack. Because different ECS prefixes can bypass a query aggregation, attacker can trigger many queries and easily collide, spoof the responses. Our draft updated this RFC to enforce a no ECS support state tracking mechanism per zone, allowing reservers to safely aggregate queries and close the gap. To wrap up, vendors are actively patching these ambiguities, but without standardized guidance, new implementations will face the same issues. That's why we brought 6 drafts here, and we welcome any feedback, including technical approach, draft structure, or anything else. All the 6 drafts are on the data checker, and please don't hesitate to reach out. Thank you.
All right, thanks, Yushi. We have a minute for any questions or comments. All right.
Thank you, and please reach out to Yushi if you have further questions.
We got Deepak up next. I'm going to share his. We got Deepak up next. I'm going to share his slides here.
Yeah. Yep.
Okay, Deepak, and then I'm going to start a timer for 10 minutes so we can see what's
Yeah.
going on. And, then, and we can hear you,
Slides.
so I think you'll be ready to go as soon as I pass control to you.
Yeah, I'm trying to get the controls. Can you please allow me the controls to move the slides? Yeah, there we go. Yeah, awesome. Sounds good. Hi, everyone. Thanks a lot for inviting me. And I'm Deepak. I'm a computer science PhD student at Georgia Tech. And today I'm going to talk about our work, Are You RPK Ready? And this work was published at IMC 2025. And this was done with Roma Fountain from IAJ and my advisor, Cecilia. So in this talk, I'm going to discuss about the prefixes which are currently not covered by RPKI route origin authorization certificates. We'll characterize these prefixes and we'll try to understand what will it take to get these prefixes into RPKI. And I'll also introduce a platform which will help us in this process. So BGP, the Border Gateway Protocol, lacks built-in security mechanisms to verify the routing announcements. And RPKI offers us a mechanism to validate certain set of like BGP announcements, certain parts of the BGP announcements. So the way RPKI works is the internet registries, basically the RIRs, they assign a public and a private key pair, basically a certificate to an organization who holds resources, internet resources like IPv4 or IPv6 or ASS, in fact. And now organizations can use their private key to issue these certificates called ROAs, or Route Origin Authorizations, where they authorize a certain ASN to originate a prefix in BGP. Now we have a record where which ASN is authorized to originate a certain prefix in BGP. And now other networks in the internet, they can take these ROA certificates and the public key, and they can use this public key to verify the certificates and then take routing decisions accordingly. And RPKI has been around for a while, more than a decade at this point, and several works have looked into the adoption of RPKI, the benefits of RPKI. Large organizations like Google, Amazon, and all of the big tech, they have adopted RPKI also in the past. So there is actually a consensus that RPKI is actually beneficial. And when we look into the data, it also shows in the past 6 to 7 years, RPKI adoption has grown multifold. In IPv4, the adoption, in both IPv4 and v6, more than 50% of the routed prefixes are covered by RPKI certificates at this point. So the question is, what about the remaining prefixes? So what will it take for the prefixes that are still not covered by RPKI? And if you look into the IPv6 trend line, you can notice that in the past year, the growth has almost saddled. IPv4 is still growing, but can we expect a similar rate of growth for the next 50%? So that's something that we'll look into this in this presentation. So this is the question. So how can we support the RPKI adoption for the remaining 50% of the prefixes? I'll skip the slide over, but at this point, RPKI is a mature technology. So we would be expecting, like RPKI adoption should be fairly straightforward since everyone is adopting RPKI, right? But turns out the reality is different. Organizations adopting RPKI do face a lot of complex issues. And these issues can be technical and also non-technical. Let me run you through an example. Suppose we have this prefix. It's a /21 IPv4 prefix with an origin ASN. So the first question, and currently it's not covered by RPKI. So the first question arises is, who can actually issue the ROA certificates for this specific BGP announcement? The answer is not very straightforward. But if we dig into like who is records, RPKI certificates, you can actually locate which organization can issue RPKI certificates. We detail the methodology in the paper, but turns out Co-location America has the authority to issue RPKI certificates. So can we just poke this organization that, please issue the certificate, and they'll just do it? Again, it's not very straightforward. The reason being, what if this specific /21 announcement has more specific router subprefixes? Now, if you issue one RPKI certificate for the /21, it will invalidate these more specific announcements. Now, if you look closely, it has 5 router subprefixes, and all router subprefixes have different origin ASs. So if you have different origin ASs right now, you need to make 5 more ROAs. First of all, you need to create these 5 more ROAs, and then you have to go back to the /21 ROA. Now, the complexity just increased. To go one step further, if you look a bit more closely, this /21 prefix has actually been reallocated by Co-location America to another company, which is Internet Utilities North America. Now, Co-location America can't simply just issue the certificate by themselves. They have to give a heads up to Internet Utilities, discuss with them, and this inter-organization communication is again something that doesn't happen very in a very straightforward way. So issuing RPK certificate certainly just gets much more complicated. So for an organization who is trying to plan how should I issue these ROAs, like what are the factors that I should consider, especially it impacts like the smaller network operators. So what are the questions that they should answer and in what order, how they should plan ROAs? So to help these people out, we created a framework where we put together all of the questions or the factors that an operator must consider while planning ROAs. We put them in order, and an organization can actually look into this framework, which will help them guide in the ROA planning process. But just having this framework is not enough. So to answer these questions, operators also actually need the data as to, okay, do I have the authority to issue ROA? If not, what I should do? What are my routing characteristics? So a lot of factors, a lot of questions still might also remain unanswered. So we put together public data and create this platform where an organization can actually answer these questions, and it will guide the ROA planning process. So in this platform, an organization or an operator can search for a prefix, they can search for ASS. We also offer API access. And to give you a quick look into what all data we provide, when you search for a prefix, we actually inform you which organization has the authority to issue these ROAs, what are the customer organizations that are involved, and are there any routed sub-prefixes? So if you have these routed sub-prefixes, you should be more careful. So we also have this tab called Recommend ROAs, where you search for a given prefix. It'll actually list out all of the ROAs that you need to create and in what order, what should be the configurations also. So now a network operator can actually gather all of the information and follow the framework, which will help them guide in the ROA planning process. Now, once we have this platform and we have this data, let's characterize all of the prefixes which are currently not covered by ROAs. So this Sankey diagram is for V4, routed V4 prefixes. I'll start with all of the prefixes which don't have ROAs, covering ROAs. That's my 100%. So turns out 21% of these prefixes are not even in RPKI. We'll come to that later. But 80% of prefixes are in RPKI. So basically, the organization has signed up for RPKI, and there's a certificate which can be used to issue ROAs. Now, there's a spectrum of the degree of difficulty to issue ROAs out of these prefixes. So on the easiest side of the spectrum, we have almost 50% prefixes, which are currently not covered by ROAs, but there's very low technical barrier into issuing ROAs. For instance, there are no routed sub-prefixes, there are no customer organizations involved, and there's very low technical barrier into issuing ROAs. In fact, a big fraction of prefixes are managed by organizations who, in fact, have already issued ROAs in the past. So it's not like they're unaware of RPKI. And these prefixes are managed mostly by China Mobile, China Education Research Network, Korea Telecom. And on the middle of the spectrum, there are a bit of complications, but our platform can help organizations. And on the other end of the spectrum, on the most difficult side, we have 20% prefixes currently in ARIN, managed by organizations such as Department of Defense, USAIC. These organizations haven't even signed up for ROAs. So they don't even have a certificate using which they can issue ROAs, and there are certain policy barriers to it. And getting these 20% into RPKI is much more difficult. So to summarize, ROA coverage for the next 50% of prefixes won't be as straightforward as the first 50%. But also there are non-technical aspects that impact ROA adoption. So we need continued support and training and more focused efforts into getting these prefixes into RPKI. And our platform, RU RPKI Ready, will definitely help us in this phase, in this process. And here are the links to the IMC paper and the dashboard. You feel free to check into it. We also offer bulk data access on GitHub, API access, and you feel free to send me a message and email. Thanks, everyone.
Thanks, Deepak. We got time for a question or two. Either raise your hand in the Meet Echo or come up to the mic if you want.
Yeah.
Okay, look, I don't see anyone in the queue right now, so thanks so much for fitting into the time, Deepak, and meeting us on a funny time zone for you.
Yeah, thanks a lot for inviting me.
Bye-bye. So next up, we have Wei Tong here in person. And Wei Tong, I'm going to bring your slides up. No, what's called an unveiling in there? What did you?
This one.
Yeah. All right. And I'll pass the slides clicker to you. All right, you're ready to go, and you have 10 minutes.
It's the timer.
Yeah.
Yeah. Thanks for the. Yep. Thanks for the introduction. I'm Wei Tong from Virginia Tech, and today I'm presenting our work on how we measured our deployment and dependency between different ASICs. This work has been accepted to IMC 26 and is from Virginia Tech and Cloudflare. So let's first have a quick review about the RPKI. So RPKI takes two parts. The first is the resource owners who control the AS numbers and perfect. They need to create a crypto certificate called ROA. And then in the router side, they will install the RV and doing filtering based on the ROA certificate. So there's two questions for us to understand how the RPK are used and how RPK protect today's internet. Firstly, is how the network operators use the ROA, which has already been answered last presentation. And the next question is about how the network operators use RPK to filter invalid BGP announcement, which is deploying RV, which is not that quite straightforward because the RV policy is not publicly available. So there's some previous attempts. Firstly, takes a very simple example is the BGPSavior.com project by Cloudflare. And what they do is that they use RPK valid perfect, RPK invalid perfect, and test the connectivity for each client on these two destinations. So if you can visit the valid one but cannot visit invalid one, you are protected. And also there's some like crowdsourcing attempts, collecting all the blog posts, all the stuff. So we also try to measure the RV, we call it RV protection, whether one network can reach to RV invalid sources by running some in the web invalid perfect and some side channel technologies. And we publish this measurement result every day. But there's also a challenge on the existing data plan measurement, which means all these measurements relies on RPK invalid perfect. But with more and more ASICs deploying our way, we are seeing less RPK invalid perfect today with very large globally visibilities. So in short, so one RPK invalid perfect will be filtered in all RV ASICs, which means that more ASICs deploy RV result harder to measure the RV deployment. So that's the challenge. So our idea is that imagine a world that everyone doing RV, then we cannot measure anymore. So can we make our perfect only filtered by one or more RV ASICs? So that's our goal. So let's quick look into the RV ecosystem. Firstly, we have the publication point where the raw object being stored. And then we have validators or relying parties who fetch the ROAs from the publication point and then giving to the routers. So instead of letting the RPs fetching all the raw object, what we're going to do is that we create our own publication point on the area. So then all the relying parties need to connect to our publication point. And this relying party will give what they see to each ASIC and doing RV. So instead of giving rules to all the RPs, so what we are going to do is that we give different rule to different relying parties. So we only give this very specific rules that will invalidate our announcement to only one RP or only one validators, which means that only the AS1 we are seeing our measurement perfect as RP can invalid and filter it. For all other ASs in the world, they're seeing our BGP announcements all as valid and will not filter it. So by doing that, first using a divide and conquer methodology, and then running data plan measurement, we can actually tell who is deploying RV, and we can tell which ASs are relying on which relying parties. And although the methodology is a little bit straightforward, there's still some very tricky things we need to solve. So in major cases that we have the upstream AS1 and the downstream AS2. So there's different kind of possibilities that these two ASs deploy our way. The first is these two ASs both deploy our way using different RP servers. And then we could see that if we only gave our special rule to RP2, then only AS2 will drop it. AS1 still keep the connectivities. But also, maybe the two ASs were using the same relying parties. And in these cases, once we gave the invalid rules, then these AS1 and 2 were both being disconnected. And also, because of the in the past filtering, once the AS1 received invalid the rule to invalid our announcement, AS2 will be blocked immediately at the same time. So the challenge is how we differ the shared reliable party with the option filtering. So here's our methodologies. So because of if the AS1 and AS2 using the same relying parties, and what's going to happen is that the AS1 and 2 will not fetching the content from the relying party at the exact same time every cycle, because there's a fetching cycle between the relying party and the routers. So maybe in T0, we see the AS1 and 2 will be blocked at the same time, but maybe the next cycle, we see the AS2 will be blocking our pings earlier before the AS1. And if there's a scenario of option filtering instead of sharing relying parties, which means AS2 are not fetching directly from the relying parties, then what we're seeing is that AS1 and 2, we are blocking our ping traffic at the exact same second every time. So we run our experiment, but firstly in IPv6, because we are using a lot of IPv6 perfect, and we're measuring 20K ESs, and we found out among these 3,000 ESs being protected, there's only 1,000 ESs actually deploying RP themselves. Remaining 2,000 are just protected. And also we found out the more than half of ASs are only relying on one RP server, although the RC recommend to use at least multiple RPs for the redundancy. And only 14% of these ASs are deploying multiple RPs across different AS numbers. And also we found some interesting case for a couple very popular RP servers like the Cloudflares and NTTs. And we also compare with what we're seeing with the Comcast RP, which is non-public. And we see that, for example, Comcast, because all the ASs rely on Comcast are just option filtering. So we are seeing that they are blocking our traffic at the same time as the black bar. But for the Cloudflare, they are blocking our traffic at totally different times. And then we are comparing who is actually deploying our way with the AS rank, and we found out the higher rank ASs are mostly deploying our way themselves, while the lower rank ASs is mostly benefit from their options. And in summary, we present this R-scope measurement framework. We run the measurement from the last year, but mostly in IPv6. But we are also working on the IPv4 measurement to cover all the internet. And we will release our measurement result soon, maybe next week. And our paper will be published in this year's IMC in October.
All right,
So-
thanks, Wei Tong. We've got a couple minutes for questions or comments. To put yourself in there in the queue if you'd like to do that. Wei Tong, are you going to have a preprint of this available, or so he's before camera ready? You had about a month or something before camera ready. So if you have feedback on the paper, you have a chance to get it in there. Do you know if you're going to do a preprint?
Yeah, so we are working on the camera ready, but the deadline is still, we have some time.
Okay.
Please, as soon as you're ready, send a link to the paper to the mailing list.
And we have Deepak in the queue, so I'm going to go to him.
Yeah, like a quick question.
There you go.
So the RC recommends networks to use multiple relying parties. So if going ahead, if every network out there, or especially the big networks, if they are using multiple relying parties, they might have different policies on to coming to a consensus if they are getting different ROAS for the same prefix. So would that introduce some sort of noise in your inference?
So there's different ways that one network can deploy the multiple RPs. So whether they are just in separate place and combine them together in the VRP level, or they are using, like, we must use the VRP only if it's being consistent across different RPs. So in the later way of deployment, certainly we cannot test all the combinations of all the RPs, but we are trying to test some kind of combinations, and we confirm that at least there's a couple 30, 40 ASICs they're actually doing this consistent need kind of deployment. Thank you.
Awesome. Sounds good.
Thanks, Deepak. Thanks a lot, Wei Tong. I'm going to switch over to Yejin Cho's slides next. She is remote. That's our last remote presentation for today. Just give me a minute, Yejin. All right, you are. Okay, there's your slides, and let me pass control to you. You should be ready to go, and I'll set the timer for 10 minutes, and you're all set. Go right ahead.
Hi, thanks for inviting us. My name is Yejin Cho, and this was a joint work with John Heidemann from USCI site. So our topic is what IPv6 RFCs don't say about VPNs and how missing guidelines led to IPv6 depreference in the VPNs. So thanks to multi-decade efforts of many people, IPv6 been growing steadily. But the problem is that having IPv6 doesn't really mean that IPv6 is actually being used. As you can see in the graph, there's a gap between IPv6 capable and IPv6 preferred. So we named this phenomenon IPv6 depreference. When the client has IPv6 support, but IPv6 is depreferred over IPv4, the client chooses to use IPv4 instead. And normally, due to Happy Eyeballs algorithm, IPv6 should be preferred over IPv4. So the problem we notice with that VPNs, V6 is often depreferred severely. The baseline would be non-VPN users. They use IPv6 most of the times, like 82%. The VPNs, we name it good VPNs, they have similar IPv6 usage, around 73%. However, the preferred VPN users often don't use IPv6, like 22%. And to approach depreference, we investigated 40 million visitor logs that included visitors from 123 VPNs. And we were able to see that some VPNs depreference heavily, while some VPNs are fine. So what we figured out is the interaction between prioritization rules and how the VPNs configure interfaces would collide and end up in deep preference. So when we talk about prioritization rules, it's about RFC 6724. This rule prefers IPv6 GUAs over IPv6 ULAs for source pair destination. And there will be IPv4 public and private. And then IPv6 ULAs would be less preferred compared to other pairs, as ULAs are not supposed to reach outside of the local network. So devices would have multiple interfaces, and we were able to see that VPN users always select B4 address as source address. So we bring up an example of mobile VPN. We can see that they assigned IPv4 private address and IPv6 ULA address for users on their interface. And we know that because of the prioritization rules, B4 private would be preferred as a source address compared to V6 ULAs. This means that IPv4 is selected as a protocol. So why does deep preference happen? So by design, IPv6 is supposed to be pure. ULA source address means that this traffic never reaches outside of the LAN because that will not happen. However, VPN implementers often carried over the IPv4 design assumptions, like equivalent of V4 private is V6 in V6 ULAs. So I thought deep preference was sort of surprising because there was no explicit guideline that explained that this behavior would happen. And no IPv6 RFC specifies which address type should be used as a VPN inner tunnel source address. Thus, implementers had to infer this behavior, which was not easy. So we bring up 4 possible solutions, and we have our recommendations as well. So the first one would be assigning VPNs assign each user a unique GUA address on their interface. So if you do this, the pros will be that address will have actual meaning, which can be linked to a specific user. But the downside is that complexity of managing address allocations without much purpose, as VPNs tend to handshake in different ways. So the second solution would be VPNs assign a shared static GUA address. This is very easy to implement. They just have to embed a static IP in their code base. But the problem is it's quite unclear which one they should use. For instance, we were able to see that this VPN code VPNly implemented using IPv6 documentation prefix, which is not the best use of that prefix. So the third solution would be creating a new address class called tunnel local address. This is our suggestion, and this address is to specify that this traffic is being tunneled through, will be encapsulated later, and thus should not be deep preferred. And luckily, we have the remaining half ULA space, which is unused currently. The pros will be that this actually represents a traffic. The downside would be difficulty of adding a new class. So if TLA is possible, it will be very similar to Teredo. Teredo was IPv6 over UDP over IPv4, and this address class indicated that IPv6 this packet will be Teredo later by the Teredo client. And the fourth rule will be changing the prioritization rules. This would have some pros that there's no need to change the VPN code base, but it might break a lot of things because ULAs are supposed to be ULAs. We were able to see that a lot of VPN users, because they want to use IPv6, they were changing their etc gai.conf file, which basically implements the RFC rules. So yeah, some users are doing this. So the conclusion is that IPv6 has been deep preferred in VPNs. We have suggested a lot of solutions, and we need a lot of inputs from RFC writers, IPv6 experts to how to solve this issue. Yeah, thank you.
Thanks, Yejin. We've got a few minutes here, and we have Lorenzo in the queue, and I'm going to join the queue also, not in my chair role, but feel free if you also might be able to help with this. Let's go to Lorenzo.
I can do this. So I think I think you should think about which of these solutions, if any, preserves the advantages of IPv6 or IPv4, which is basically end-to-end connectivity, right? So that's one thing. I think basically just number one has that property, I think. And so if you don't do this, then you have a bunch of NAT state that you have to maintain on the server, and you don't have end-to-end, which seems bad. Yeah, I'd rather have like v4 only VPN at that point. The other thing that you might want to consider is that there's an RFC. It's a best practice that says it's about assigning IP addresses to general purpose devices, RFC 7934. And it basically suggests providing a /64 or other mechanism that allows a client to create as many addresses as it wants. I think /64 is ideal because then the VPN can be used to extend the network to devices behind it. The other thing that you could do is, if you control the servers, you could just run DHCP-PD. You don't have to like communicate this stuff inside the VPN at all. Now I don't know that that's not how VPNs work. I know that IKEv2 has this, but anyway, I would say I don't know if /64 is one of these. If it isn't, I would say that's number 0, and you should do that. But
So I believe the problem is that basically VPN providers want to preserve anonymity by multiplexing the traffic between a lot multiple users that uses single 128 address, not. So if you give a prefix to this person, using a prefix, this person will be able to be narrowed down. So yeah, it just goes back to the end-to-end versus VPN discussion. Yeah, but I believe there should be a better
yeah,
solution.
you can, if you want to do a shared 64, that's probably okay as well. You basically mix a bunch of 128s between different users. I mean, technically, you still have a tracking problem there. It's better than with the /64 because anyone who maintains state will have to maintain state on the whole 128 bits. But I'm using up time from the rest of the queue.
Thanks, Lorenzo. I think it'd be great if you guys followed up afterwards. I'm going to kick myself out of the queue. However you do that, and let Suresh go. Suresh, why don't you?
Yeah, thanks. I think like Lorenzo said a lot of what I wanted to say, but I think one thing is like take this to 6-man, because if you really want to go down this path of like creating a new class of stuff, 6-man is the right place to go. Like you cannot just say, hey, we'll take half of the ULA space. It's not something, because we have, I think the other thing was previously allocated for centrally assigned ULAs, right? And it needs to go through protocol action. And it also requires probably some changes to address selection, which is also like a 6-man matter. And we've spent years getting this right, and you should look at like how you specify this based on the address selection rules for v6. Thank you.
Thanks, Suresh. Thanks so much, Yejin. So of course she's remote and you're up really late, so thanks for joining us. Get in touch with her directly if you want to talk about it this week. I'm also interested in this, so I'm happy to talk and relay my understanding of it to Yejin to help with her project. So up next we have Shibo with the first or the last of the 3 talks today that are from IMC. So you can come up and I'll share your slides. Okay, you should have control now. You're ready to go.
Hello, everyone. I'm Shi Cui from Tsinghua University. Today, I will introduce our team's measurement study on intermediate paths of email delivery. So in the original design, people can independently deploy their email services. In such cases, an email travels from the sender's client to the outgoing server and is finally delivered to the incoming server. However, situation changed. With the rapid development of cloud services, hosting-based email have been largely adopted. So as a result, the traditional end-to-end email delivery model is undergoing change. Figures show the email delivery process, including intermediate servers. Email from the sender's client pass through one or more middle nodes before reaching the outgoing server, such as hosting providers, security providers, and email signature providers. So therefore, the email delivery paths show a segment-to-segment mode. We define the middle nodes as the relying server located between the sender client and the outgoing node. As a member of the email path, vulnerable middle nodes affect the security of the entire email delivery path. Attackers have already used the dependency of these nodes to carry out malicious services. For example, echo spoofing allows attackers to exploit the relaxed source restriction of email relays in the intermediate path to spoof victim domains. Finally, it can lead to distribution of millions of phishing emails. Previous works focus on incoming and outgoing servers in the delivery path. They measured centralization by collecting data from MX and SPF DNS records. However, these studies lack visibility into middle nodes in the path, so the dependency and potential risks associated have been overlooked. Therefore, our work aims at analyzing the landscape of email intermediate paths. We use the received headers to understand the email delivery path. It records each node that an email passes through from the sender's client to the incoming server. So it has two key components, the front part and the back part. The formal part records the information of previous node, while the later one records the current node. So this figure shows the process of our construction of the email intermediate path dataset. First, obtain received header from a large email service provider. Second, generate a template library to pass the received headers. And third, build and filter the media paths. Our received header data set comes from a large email service provider in China, Mail. It offers email services for more than 20,000 organizations. We only exact the minimum data required for our study and did not obtain the user's exact email address or body. So in the 9 months long logs, we collected a total of 2 billion emails. To pass the headers, we built a template library with 54 regular expressions, which can match 96% of received headers in our dataset. By using the template, we can extract the path nodes. Given that email servers may hide or forge their identity, we use the front part of the received header to indicate the information of their previous node. So through this process, we can construct the delivery path from the email. We further filter the email delivery path to use some criteria, including spam flag, SPF verification without middle nodes, incomplete path, and more. Finally, our dataset involves 105 million emails. 1/3 of them were transmitted within China. This unique dataset allows us to address the following research question. First, what are the identity and distribution of email middle nodes? Second, what is the dependency structure and the regionality of email intermediate passes? Third, what are the centralization degree and cross-country differences of email intermediate passes? We find that most middle nodes belong to email service providers, as Outlook.com accounting for more than one-half of the emails. Among the top 10 providers, we also identify domains offering email signatures and security services. To better understanding the delivery path structure, we define the dependency patterns from two perspectives. First is the hosting pattern. It describes the relationship between middle nodes and the sender domain, reflecting the extent to which a domain relies on a third-party provider. So it includes self-hosting, third-party hosting, and hybrid hosting. We also analyze dependency patterns of country domains. We find that proportion of third-party hosting in email intermediate passes for various countries more than 60%, highlighting the email dependency on hosting providers. However, intermediate passes from Russia and Belarus shows the self-hosting proportion of about 30%. The email intermediate path involves different SLDs, meaning that the dependency may pass between various providers. So we analyze the dependency pathing pattern in 9 million multiple dependency intermediate paths. If two email intermediate paths contain the same set of middle node SLDs, we consider them to belong to the same dependency passing relationship. Therefore, in total, we identify about 30,000 dependency passing relationships, among which 56% involves two SLDs and 80% involves more than 3 SLDs. So we can see that a significant proportion of these emails rely on Outlook for transmission. By analyzing the top 50 dependency passes, we identify 6 common types of passing relationships. So we find that most common dependency passing occurs between email service provider and the email signature provider. Moreover, we analyze regional dependency of email intermediate paths. We focus on analyzing the dependency from domain of different countries or continents on external regions. We suggest that stakeholders should pay closer attention to critical points of the dependency along intermediate paths, so they may pose significant risks of service disruption. This figure shows the regional dependency of email intermediate paths in 60 countries. So if email media nodes belong to the same country as the sender domain, is marked as the same. We find that regional dependency patterns vary significantly. In some countries, over 90% of email intermediate paths rely only on domestic infrastructure, such as Russia. However, in some countries, email intermediate paths almost entirely depend on foreign infrastructures, such as Morocco. Furthermore, we try to analyze the reasons behind. We find that countries belonging to the Commonwealth of Independent States significantly rely on Russia's email infrastructure. In contrast, no other countries show a similar dependency. Moreover, we observe that email intermediate passes often reflect dependencies between geographic proximate or linguistically similar countries. For example, 68% of email passes from New Zealand include middle nodes located in Australia. We also analyze the dependency at the continental level. As shown in the figure, The majority of emails originated from Asia, Europe, and North America have middle nodes located within the same continent. In contrast, South America are highly dependent on North America. We use the HHI index to evaluate the market concentration of email middle nodes. A higher HHI indicates a more concentrated market structure. So given all the email intermediate passes, we obtain an HHI of 40% for the middle node market, which indicates a higher concentrated market. Microsoft donates the overall email middle node market, participating in about 70% of email intermediate passes. So this figure presents the HHI of middle node providers across different countries, with the largest providers marked by a circle. So we find that HHI varies greatly. Outlook donates the market share in most countries, typically more than 60%. The exception is that Yandex is the primary provider in Russia and Belarus. So in conclusion, using a unique and large-scale industrial email dataset, we enable middle nodes and intermediate paths of email delivery. We analyze hidden dependency and evaluate the centralization degree of the email intermediate paths. We have already published our code and dataset for help future research. Thanks for listening.
Thanks. We have time for questions or comments. Anything? I don't see anyone in the queue, Shibo. Thanks for joining us.
Yeah, I just want to say I announced your talk on a couple of email-related mailing lists, and it spurred already some discussions. So maybe there's more people reaching out to you after the meeting.
All right, so up next we have Ming Ming, also an IMC talk, and happy to have her here in person, someone who wasn't at IMC in the US last year. Let me get your slides up.
Hi everyone, I'm Mingming Zhang from Zhongguancun Laboratory. Today I will talk about the multilingual internet. Our recent measurement study published on MC25 sent a wake-up call that is integrating internationalized content in X509 certificates creates compliance gaps and complications that need to resolve. The public key infrastructure is the security foundation of the internet. It relies on X509 certificate to bind identities to cryptographic keys. These certificates need to follow some strict standards that define the required format, structures, and encodings for every single field. The multilingual internet is driven by ICANN and the Universal Acceptance Initiative, which ensures internet applications and systems can properly handle characters beyond the printable ASCII sites, like Chinese characters. So when an X509 certificate contains any of the internationalized content, such as the IDN, IRI, or multilingual text, we call it a unicert. So why unicert? Can unicert break things? Because the broader Unicode space complicates the issuance, parsing, and validation of certificates, which may introduce potential security or usability issues. Many real-world incidents have shown that improper Unicode handling in certificates can cause cert spoofing, incorrect attribute parsing, or even buffer overflows in client software. However, while X509 standards support Unicode, the universal acceptance readiness of PKI's core mechanism remains largely untested. So this is the gap we aim to fill. Our study presents the first large-scale measurement and empirical security study of Unicert. It's guided by three research questions. The first is, have certificate authorities issued Unicert in compliance with the complex standards? The second is, do mainstream TLS implementations correctly parse Unicert according to normative constraint? The third one is, what are the security and usability impacts of non-compliance issuance and parsing flaws? So let's start with the Unicert issuance. The first challenge we meet is identifying a definitive standard. How can we establish clear normative requirements for Unicert compliance? The problem is that relevant specifications such as X509, DNS, and IDN spec suite, and also CA browser baseline requirements are highly interdependent and evolving. There are many updates, revisions, or references here. In addition, many rules for format or encoding of certificate fields are scattered across natural language, the footnote sets, or ASN1 definitions. So compliance violations may arise from any of these aspects. To tackle this complexity, we employ RFC GPT, a custom GPT augmented with RFC database to navigate complex requirements and constraints. It helps us identify encoding, structure, and character constraints for cert fields that allow non-ASC characters. We have instructed 95 rules covering 36 cert fields with 50 rules missing from existing compliance checks. These rules are the foundation of our measurement study. We use this rule to build a certificate checking link and use it to check against over 34 million Unicerts collected from the CT database. So let's look at the Unicert issuance ecosystem. These Unicerts were mainly came from about 700 organizations, and the issuer numbers are clearly rising, showing that the adoption of Unicert is steadily growing. From this set, we have identified about 250,000 non-compliant or problematic Unicerts, and 65% of them were issued by publicly trusted CAs. These issues mainly fall into three categories. The first is improper character checks, which involves basic flaws, such as including the non-printable characters in the printable string field. The second is a lack of value normalization, such as the UTF-8 string not normalized to Unicode NFC form. The last is invalid format or structure, including the formatting errors or invalid encoding methods or any other structural issues that hinder the certificate parsing. These non-compliant Unicerts were issued by over 500 organizations, indicating that the problematic practice is widespread, involving both major global CAs and regional providers. Meanwhile, we also found some requirements may not have been fully covered by the existing linting tool that CAs currently use. These issues are not just limited to one or two fields. Actually, we have identified that the 17 different subject or extension fields that didn't follow a relevant standard or baseline requirement. There is an interesting case study. We know that DNS names are critical for identifying peer entities. However, we found 27,000 Unicerts with malformed IDNs in the DNS name field. Many Punicode IDNs are syntactically allowed under the current CAB baseline requirements. They have valid P labels and they are resolvable well wildcard DNS. However, when we decode them back to the Unicode, we found there are many special characters in the domain labels that are disallowed by the relevant standard. So there is a conflict. The CAs appears to conflict with the relevant baseline requirements, but the resulting certificates are problematic, maybe dangerous for user agent that needs to parse or use these domain names. The next question is, do TLS libraries respect declared encodings and enforce strict character checks? We ran a gray box testing for 9 TLS mainstream libraries, and we crafted test Unicerts with a variety of Unicode blocks and encoding tabs to check whether their passing APIs can properly handle this special Unicert. The results reveal a wide range of decoding or character handling anomalies in all of our tested libraries, including the incompatible or overtolerant decoding, such as using non-standard declared method to decode or accepting characters beyond standard range. We uncover some passing flaws that may enable exploitations. For example, the encoding and decoding mismatches might allow common name forgery, and improper replacement of control characters could enable CLL spoofing. We did find some certificate in city logs that could be misinterpreted like this, but we have no evidence of real exploitation yet. Finally, we also conducted an empirical study in the real-world scenario and uncovered some interesting threat services. The first threat is misleading city monitoring. We found malicious or compromised CAs can exploit parsing inconsistencies to make CT monitors misforge certificates, which allow the concealment of some deceptive identities. The second is about user spoofing. We found a specially crafted search field can manipulate how browser warning pages are displayed. For example, the Chrome's warning page can render bidirectional characters in the malformed common name field. And Firefox page could show misleading information that is derived from a malformed SAN field. This will potentially trick users into trust unverified sites. So to sum up, achieving a truly internationalized PKI is currently challenging due to the systematic issuance non-compliance and universal passing flaws. We consider building an internationalized PKI requires collaboration work among CAs, TLS developers, and the relevant standard bodies. We have provided some checking rules, tools, and recommendations to the community to help better handling of Unicert. We hope to bring us closer to a much secure and global PKI. That's the end of my presentation. Thank you.
Thanks, Ming. We've got a couple minutes available if there are questions. Get yourself in the queue.
Yeah, maybe I can ask something quickly. I mean, thank you for doing this work and detecting these problems and digging into the security-related aspects of it. Did you reach out to any of the issuer and organizations to point them at these problems?
We have disclosed some of the issues to Let's Encrypt and some other CAs and talk about the handling of IDNs in the cert, but some technical managers, maybe they think they have followed the current baseline requirements and technically they perform right, but this mishandling of IDN should be reconsidered by any other groups like the DNS groups and the TLS group to working together to reach
Agreement.
agreement. Yes.
Okay, more work for us. Thanks.
Thank you.
Could you introduce yourself?
Yes, this is Lieven from IETF. So I have a question. Could you go back to slide 22?
Okay.
So I think you mentioned that this vulnerability can be exploited to cause some damage in certificate transparency monitoring, right? So did you already find like a existing exploit, or is just some kind of assumption that it could be used to do this kind of damage?
No, we didn't find any real world exploitation. So this is just in the experimental assumption. We verified that some city monitors like some major city monitors can have mishandled some of the special characters and they can't search or render the results through their APIs. So we consider some malformed certificates will be concealed because of their implementation flaws.
Yeah, okay. Thank you very much. Yeah.
All right, thanks much, Ming. We have Zhenchen up next to take us to the end of the meeting.
Hi everyone. I'm Zhenian Huang, a PhD student at Tsinghua University. It's my great honor to present our work, measuring the time source vulnerabilities in the NTP EL system, which was published at IMC 2025. First, let's briefly review the background of NTP. Accurate time plays a vital role in the internet security, such as TLS and RPK. The network time protocol, or NTP in short, is widely used to synchronize time between different computer systems on the internet. While NTP serves as a critical internet infrastructure, it was not initially designed with security considerations, making it suffer from various attacks, such as time-shifting attacks. In such attacks, adversaries could manipulate timestamps in the NTP response or control NTP server to send malicious timestamp to clients. Therefore, as one of the essential mitigation strategies against the time-shifting attacks, the network time security, or NTS in short, has been proposed to protect the authenticity and integrity of NTP packet. In NTS, server sends response using server to client key, and the client uses a key to validate the response. However, NTS cannot judge if the NTP server itself is providing inaccurate time and inaccurate time sources to propagate errors time information to clients. To evaluate the degree of timing increase with the NTP EL system, we first collect open NTP servers on the internet from April 2023 to August 2024. We conducted 66 rounds of scans at weekly intervals. We found around 7 million open NTP servers, 3,000 NTP pool servers, and 21,000 IEFD servers. The IEFD server is indicated by the IEFD field in the NTP response to provide time to clients. We also collect open NTS key servers on the internet. From December 2023 to August 2024, we conducted 9 rounds of scans at monthly intervals. We found 583 NTS key servers, 8 times more than the NTS key servers on the public list. Based on the measurement data, we first analyzed the characteristics of NTP server. We found 1,115,000 open NTP servers, 7 NTP pool servers, and 1,000 IEFD servers are by timekeepers. That is, their times have an offset greater than 10 seconds from UTC. In words, while stratum 0 clocks, such as atomic clock and GPS clock, are traditionally to be considered to be highly accurate time, we found 61.2% open NTP servers and 10.8% IEFD servers utilizing stratum 0 clocks are by timekeepers. We then analyze the configurations of NTS servers. We found even the number of NTS servers is on the rise. 374 NTS key servers are misconfigured, hindering their ability to provide time services. For example, 24 NTS key servers use expired or self-signed TR certificates. 335 NTS key servers are associated with NTP servers that are unable to provide correct time, and so on. We then analyze the causes of bad timekeeping. We found 92.1% open NTP servers suffer from synchronization anomalies, such as packet loss, while 6.7% open NTP servers use low-quality time sources, such as they use inaccurate time servers. To better understand how NTP server configurations affect the time accuracy, we launched anomaly surveys to 377 NTP operators and received 40 email replies. We found they also appearance the interference point time sources and unexpected packet loss. For example, for operators providing inaccurate time use low-cost GPS receivers, 3 operators experienced packet loss due to the improper firewall configurations and SP security risk. Based on the measurement results, we uncovered 2 security risks stemming from flawed NTP server configurations. The first is single source vulnerability, as shown in the figure. An attacker first manipulate time of an upstream server, such as by on-pass or all-pass attacks, such as hijacking the BGP route to the upstream server, and manipulate timestamps in the NTP response to the upstream server. After that, when downstream servers query the upstream server, they will receive and adopt the manipulated time, since they use the upstream server as their only time source. For evaluation, we find 2,024,000 NTP servers are configured with only a single upstream time server. In worse, the most the upstream servers having as many as 41,000 downstream servers. The second vulnerability is downlink IP address. I show in the figure. An attacker first control IP address of upstream server by searching for unavailable time sources. So, for example, IP address provided by the cloud service providers are suspensibly to be taken over due to the nature of dynamic IP listing clouds. After that, when downstream server queries the upstream server, it will retain a modified packet with malicious timestamps. If downstream server accepts the packet, the time will be manipulated. For conservative evaluation, we find 6,000 servers statically configure the IP address of the 37 downlink upstream NTP server, which are deployed in the clouds. For accuracy evaluation, we find 35,000 NTP servers are deployed in clouds, and 244 are now downlink. To mitigate the NTP server vulnerabilities, we have proposed some suggestions. Briefly speaking, we recommend NTP server operators use reputable and diverse time sources, ensure network connectivity, and updating time. Besides, using NTP pool as a time source is also a mitigation, since it periodically monitors time synchronization services, assigns NTP servers based on country. However, NTP pool has some limitations. The first is it doesn't support NTS, which makes NTP clients easily vulnerable to man-in-the-middle attacks. The second is its country-first NTP server assignment. The number of NTP servers varies by country, with some having as few as 4. This can lead to NTP servers centralization, introducing potential security risks. The third is fixed weights cause overloaded circles. Operator side weights are never adjusted by the NTP pool, and awaited servers get overloaded, evicted, recover, and rejoin repeatedly, causing service instability. To solve the problems of NTP pool, we propose the NTS mount, which uses publisher and subscriber model to support the NTS. To be specific, NTS mount periodically monitors the time for the public NTP and NTS servers, score them based on the time accuracy and availability, and publish a ranked list. We develop NTS mount client plugin for the widely used NTP client software, such as NTPD and Corning. It auto-fetches the NTP server list and updates NTP client configurations. Besides, NTS mount uses adaptive load adjustment, which can reduce the unresponsiveness of NTP servers. In our simulation with true NTP client query traffic, NTS mount can deliver accurate timing services even with fewer time sources than the country-based method, and reduce the service and responsiveness by 11 times and heavy query loads. We have open sourced our dataset. You can access our dataset at the KS3 website. To be summarized, We built a large-scale time server dataset through active measurements, character time accuracy in today's NTP system. Reveal that time inaccuracy is mainly caused by synchronization anomalies and low-quality time sources. Identify two security risks stemming from configurations of time sources, including single-source vulnerability and downlink IP address vulnerability. Proposing NTS MOM to provide clients with an accurate and available NTP and NTS server list. For more details, please read our paper, which was published at IMC 2025. That's all for my presentation. Thanks.
Thanks, Zhenjian. We have time for questions or comments on this work. We've got Karen in the queue. Ready to go, Karen?
Yes, I hope you can hear me.
We can.
Excellent. So first of all, I'd like to thank you for this work. Second, I think this would be an interesting presentation for the NTP working group. I just didn't get it lined up for this meeting. So I'd like to follow up with you on that. And then the third point that you made is we are actively working on adding support for NTS and pools, and there's an ongoing experiment there. I'd be interested if you were if you had to take a look at that. And that's all I had. So thank you.
Okay, thanks.
Rousing, okay. Thanks, Karen. All right, thanks, Zhenjian. I think we're done then. In Mingning's presentation, one of the follow-up questions that Miria had was about what follow-on happened. So if you think of the timeline, that IMC paper was done was presented in October, and we're about 5 or 6 months later. Maybe for the Vienna meeting, we'll almost certainly meet in Vienna. I'll think about when we have works that are published like that, if we can identify and share some of the ways they've interacted either with the IETF participants or certificate authorities or whatever, and see if we can develop some of the after effects of bringing these works together. I hadn't thought of it before, but that'd be a nice thing to do when we have that kind of stride or cycle.
Yeah, otherwise we're done. We're doing great on time this time. So thank you everybody for keeping the time. Please catch up with the speakers here if you have further questions or consider their input in your own work. And a big thanks to our note takers. That was a shared effort between Pete, Tomek, and Brian. Thanks a lot.
So see you at the social tonight and see you in Vienna.
Great talk.